Now I want to discuss some things about the boundary of the tetrahedron and how that relates to the definition of the chain complex for a simplicial complex. And so here we've got a tetrahedron with the vertices marked A, B, C, D. That kind of corresponds to a two-chain or a three-chain generator of the group C3 of whatever space this tetrahedron is living in. And so yeah, that three chain is going to be denoted by A, B, C, D. And in the definition of the chain complex for a simplicial complex, we have a rule for calculating D3 of a three simplex like that. We take you take your A, B, C, D, then you omit the first thing, which is the A, that gives you a B, C, D. Then you omit the second thing, which gives you A, C, D, but that comes with a minus sign. Then you omit the third thing, leaving A, B, D, but that comes with a plus sign. Then you omit the last thing, leaving A, B, C, and that comes with a minus sign. But remember, we've got this kind of sign rule that if you permute the vertices, then the corresponding chain it remains the same, except it gets multiplied by plus or minus 1, plus 1 for an even permutation, minus 1 for an odd permutation. So here, this minus ACD, we can rewrite that as plus ADC, because swapping the C and the D is an odd permutation which cancels out the minus sign. And similarly, this ABC we can rewrite as this minus ABC we can rewrite as plus ACB, because swapping the B and the C is an odd permutation which cancels out that minus sign. Okay, so here we are. D3 of ABCD can be written in purely positive terms: BCD plus ADC plus ABD plus ACB. And let's see what that looks like geometrically. I mean, your BCD is this face here, the face opposite A, and we've got BCD, so we would put an arrow on here, sort of clockwise, following around in the direction B to C to D, as indicated here. And remember that we could rewrite this as CDB, right? If we change the BCD to CDB, then that's a three cycles an even permutation. So that does that. The associated sign is plus 1. BCD is the same thing as CDB, and that's kind of matches up with the fact that we, instead of sort of starting at BCD and following around the circle, we could have started at C, and you get CDB following around the circle in the same way. Okay. So that's what we get for this first term here, and then the second term is ADC. So that's this face here, ADC, the one that's opposite B, and because it's ADC, we're going around in this direction. And then we have ABD. That's the face, face opposite C. I mean, remember that's it. In the definition of D3, of course, we've got four terms, one omitting each face, one omitting each vertex. We omit the vertex A, then what we got is the face opposite A. We omit B, we get the face opposite B. Omit C, we get the face opposite C. Omit D, we get the face opposite D. Okay, so there's the third one, ABD, that's the face opposite C. And we're going in it says ABD, so we're going this direction from A to B to D, around like that, following this arrow. And finally, we've got ACB is the face opposite D. It's this one here, and it's ACB, so we're going around in this direction like so. We're going around anti-clockwise as we look in. And now it's also useful to think now what will happen if we try and do D squared of ABCD. So we're going to apply, we've done this D once to get this chain here, and then we want to apply D to this again. Let's look at how a particular edge might appear in that. Okay, we look at this edge AC here. Well, it's going to occur with a plus sign as part of the D of this ACB term. Right? We've got this ACB term here. In D of that, you're going to get an AC with a plus sign, because the AC is kind of matching up with the direction of the circulating arrow. But then you also get a term from this guy here. This you've got an ADC here. So when we do D squared, we're going to get a D of ADC, and in the D of ADC, we're going to get a term CA following around the edge of this triangle in these arrows. So here we get an AC from this one and a CA from this one, and CA is the same as minus AC, so those two cancel out. So this, when we calculate D of this, the edge AC will appear twice, once with a plus sign, once with a minus sign, and they'll cancel out. And exactly the same logic applies to every other edge. It will appear once with a plus sign from one of the face on one side, and once with a minus sign from the face on the other side, and those will cancel out. So we end up actually with nothing. We find that D2 of D3 of ABCD is 0, as we expect. I mean, that's part of the proof that we've actually got a chain complex. In the definition of a chain complex, you have to have D squared being equal to 0.